So, good evening, everyone. Uh, Today we will start with the new course BM6301 Biomedical Signal Processing. So, before starting, I would like to welcome you all to NIT Rourkela. Uh, okay, and I hope all of you have settled down and you are ready to go for your studies. So, just a suggestion, uh, here's the semester goes by very quickly. By next month end, you will be having your mid semester examination, and then uh, thereafter in the month of November. So after September, you will be having in October you will be having 1 week of Durga Puja holidays, and then again 4 weeks of classes, and then you will be having the end semester examination. Okay. So the semester will fly by very quickly, and herein you will be getting a lot of assignments, okay, a lot of tests, not only by me, by all other teachers also. So you have to be very what do you call attentive, and you have to be ready for all these things. So if you feel that you will be relaxing, uh, take my words, you will not be able to relax. Okay, so prepare yourself in that way. So let's start with the biomedical signal processing. This thing. Now, coming to this part, if you look into the system biomedical signal processing, so the most basic word over here is signals. Okay, so what are signals basically? Signals are nothing but they are referred as a function that conveys information about the behavior or attributes of some phenomena. Okay, so in general, it is a function of time, but it can also be a function of space of other variables. So what does this mean? So anyone who can tell me what is a signal? Now I have given the definition. So signal is basically as over here it is written that there would be some information or attributes which will be changing over a period of time. Okay, in general. So what we have these audio signals. You listen to the musics. Okay, I am talking. When I am talking, I am uttering some information which is going to you, and this uttering of words, it is on a time scale, so it is also a signal, and we call it a speech signal. Music, we hear the music, the same thing, we have some in some beats and all these things, we have some cluster of words or information which are being conveyed to us. Okay, similarly, what we are seeing, say for example the video graphics, okay, that is a signal. Temperature signal, when we get sick, uh, our parents, they take temperature of our body at regular intervals. So we are basically measuring the temperature, which is basically the information, or you can say an attribute, which is varying over a period of time. So all these things are signals. So you can see there are different types of examples, like apart from this audio signals, visual signals, temperature signals, electrical signals. Okay, then biological signals, then we have communication signals, then we have light signals, and lastly we are having touch signals. Okay, so among all of these, what we are interested is, in this course, we are interested in the biological signals. Okay, so it may be a signal coming from the heart, it may be a signal coming from the brain. Okay, so any signals that have been generated from the biological systems, they are called biological signals. Okay, now coming to the processing. So course title is biomedical signal processing. Now what is signal processing? Signal processing is nothing but when we apply a set of processing techniques which are basically the mathematical operations on a particular type of signal so that we can extract useful information from there, we can enhance its features, or we can transform the signal in a desired way. So when we apply any mathematical operations onto a signal, to get all these things, either we extract some useful information or enhance certain feature or transform the signal, then it is called the signal processing. Okay, so herein usually the signals, they can be classified into analog and digital signals. Okay, so basically what happens is that the signal processing can be carried out either in the analog domain or in the digital domain. Okay, analog domain means in the in your first year or second year the electronics and instrumentation classes, you must have uh, made some circuits, say a simple inverting amplifier or non-inverting amplifier. Then you have put some signal through the signal generator, and in the output you are getting the analog signals, right? Now, so that kind of processing, it is called analog signal processing. Next, we have digital signal processing. In the digital signal processing, we perform the mathematical operation in the digital domain by using some microcontroller or microprocessor, whatever, any computing platform. Okay, so those are digital signal processing. So then what happens? What are the key concepts in signal processing? Some of the key concepts of signal processing include filtering, transformation, modulation, convolution, and compression. Okay, what is filtering? Yeah, you can remove more noise, or you can band limit some signals within a particular frequency range. Okay, so when we apply some techniques or the mathematical operations so that some frequency components, they can be eliminated from the signal, then it is called filtering. Transformation means we have signals in the time domain, as we have already discussed. Say for example, we represent it with x of t, where x is the variable and t is the independent variable. So over the period of time, our information content, that means the x value would be changing. Now, if we apply a Fourier transform over here, what will happen? We will get into the frequency domain and we will be getting x of omega. So this capital X is another variable. Now this variable is changing over a range of frequencies. Okay, so this is called transformation. So you are having one independent variable, and now you are applying some mathematical operations to get into another domain where the variable, independent variable, it is totally different. Okay, in this case we are going from time domain to the frequency domain. So this kind of operations, they are regarded as transformation. Modulation, I hope every one of you know about the modulations. So you must have studied in 10, 11, 12 physics, amplitude modulation and frequency modulation, right? Then comes the convolution. Convolution, it is associated with filtering, and we will be discussing that uh, in details while we cover the convolution chapter. Okay, so it is a mathematical operation which helps in implementing the filtering techniques. Okay, this is in short. Later on we will be discussing in details. Then compression. So suppose while you are recording, so previously if we had to record a signal, it used to require a large space. Okay, now what we need to do, we need to compress the signal. However, we need to compress the signal in such a way such that the information contained within the signal is not lost. Okay, suppose I take his picture. I'm having nowadays say uh, 56 megapixel, 50 megapixel camera, even in the mobile phone and all these things. So I take his picture. So when I send it through the WhatsApp, if I am not sending it as a document, then what happens? WhatsApp will reduce the size of the picture. So what it is basically doing? It is basically compressing the signal. Okay, it is basically compressing the signal. Now, the thing is that if you send the pictures through the WhatsApp, you will find that within the mobile, there is not much difference in the picture quality. However, there is a decrease in the quality. Now, if I compress a signal in such a way such that when I will try to retrieve the information, if it is not losing any information content, whatever the information content I wanted to what you call propagate, if that is not being eliminated, then I will say that it is a good quality compression. Okay, because all the original information which I wanted to share with you, it has been transmitted to you. But in many cases, what happens? You get pixelated images, right? Especially in the CCTV cameras and all these things, you will see uh, that there are pixelated things. So what are these? Those are nothing but degraded or low quality compressed images. Okay, so if you compress the image to a very large extent, then there would be pixelation. Now, in the pixelation, what will happen? You may not be able to see the face of your colleague. Okay, so over there is a loss of the information, right? So this is there, compression is also there. However, uh, it is not within the scope of our study, so we will not discuss the compression in our lectures. Okay, now lastly, applications. uh, where do we apply these signal processing techniques? In telecommunication, in medical imaging. Okay, so in telecommunication we are talking, so how it is, you are talking from one end and I am receiving the signal on other end, how it is being transmitted. You are giving some information, I am getting some information, and without getting any distortion. Okay, then in medical imaging, you will see most of the imaging systems nowadays, they are digitized. If you go for an X-ray plate, it would be a digitized X-ray plate. Okay, so what they are doing, they are removing the noises through the digital mathematical operations, right? Then audio engineering, that means you are playing with the quality of the audio by applying some mathematical operations, right? Then in control systems, uh, what happens now in the Russia-Ukraine war? Uh, they are, both the parties, they are using missiles. Okay, so how does the missile know that it has to go and strike that particular part? Okay, so there might be some environmental variations and all these things. So what you need to do, once you have set the target, the missile needs to do some manipulation in the air itself so that it can reach the target by by eliminating all the hurdles. Okay, say for example, in the case of this BrahMos and other missiles which are being developed by India also, you will see one rocket is being fired, and then from that rocket multiple rockets are being what you call emitted, so that they can destroy multiple targets. Okay, so how it is happening? You have already given the command to the missile, so it has already left the station, so it is not in your hand anymore. Now again, what is happening, when it is going into the air, in the mid air, the computational systems, they are calculating from where the targets are coming, and they are targeting those objects, right? So over there the control systems plays an important role. Then next comes the speech recognition. Okay, then comes the financial markets. So stock market, if you see, so everyone expected that due to this Hindenburg what do you call this claims, market would have gone down today, but it has not gone down today. It is, on the other hand, it is increasing. So this is also a signal, because it is a, over there the dependent variable is the price, and independent variable again it is time. So in all these areas, the signal processing techniques, they can be used to get proper results. Okay. Now coming to the biomedical signals. So we talked about these biological signals, and from there, when you come towards the biomedical signals, so what happens is that in biomedical signals, we are basically coming towards the human physiology or mammalian physiology, to be, if you want to make it a broad topic. Okay, we are not dealing with any signals from the biological systems. Here we are basically defining that the signals should be from the mammalian systems. It may be cat, it may be cow, it may be human. Okay. So in our case, we will be basically concentrating on the human physiology. Okay. So biomedical signals, they are basically the electrical, chemical, or the physical signals that are being generated by physiological processes within the human body. Okay. So electrical signals, cardiac muscles, when they contract, they will generate the electrical signals. Muscles, when they are contracting, they will generate the electrical signals. So we get the electrical signals. Okay. Chemical, when there is neurotransmission, so what is happening? Some chemicals are being released. Then those chemicals are going and exciting the next neurons, so that the signals can be transmitted. Physical signals, I am talking to you. So these are physical signals. Okay. Now, these signals, it provide crucial information about the state and functioning of various bodily systems. Okay, and due to this, the analysis of these signals is essential for diagnosis, monitoring, and treatment in healthcare. Okay. Next, what are the key types of biomedical signals? The key types of biomedical signals include the ECG. Why ECG always comes first whenever we talk about biomedical signal? You will hear that ECG, everyone will commonly say ECG. Why that is so? This is because our heart, it is a unique system where the heart muscles, they are autonomously beating in a synchronized manner. We are having two atrium, we are having two ventricles. Initially the atrium contracts, then ventricles contract, and they are working in a synchronized way. And since they are working in a synchronized way, you will be seeing that the signals are quite, they're following a, giving a proper pattern. Okay. On the other hand, if you look into the ENG signals, it will just look like a noise. If you look into the EEG signals, it will look like a noise. Okay. So whenever, so due to this reason, since we are having this electromyogram signals, which is having a particular uh, and definite pattern, the analysis of this signal is quite easy. Okay. So due to this reason, what happens is that whenever we talk about the biomedical signal processing, the electrocardiogram, in more than 90% of the cases, if you ask anyone, they will initially talk about this electrocardiogram. Okay, because whenever we basically teach the concepts using EKG, and then when the students are able to understand the basics of that, then we move towards the other signals. Okay, then we have electroencephalogram signals, which are basically the brain waves, then electromyogram, then electrooculogram, okay, then photoplethysmogram, blood pressure, spirogram, galvanic skin response, temperature, and oximetry. Okay. Now, applications of the biomedical signals, as I already told you, in diagnostics. Okay. So If someone is having chest pain, we directly go and we do the ECG measurement. Okay. Then monitoring. So if someone has undergone some what do you call this surgery, or they are undergoing any treatment, then continuous monitoring of ECG and other physiological parameters like SpO2, it may be of interest to the physicians. Then, if you want to develop any therapeutic devices, pacemaker, it is a therapeutic device because it helps us in pacing the heart, okay, so that our body gets uh, this oxygenated blood in a proper way, okay. Then wearable health tech. So we have this Apple watches are there now. These smart watches have also come, which can measure the not only the SpO2, also the heart rate and other physical parameters that can be measured, okay. So in case of last year or 6 months back, I heard that Apple Watch, it saved the life of one of the persons over there. So she fell, one lady, she fell unconscious, and the Apple Watch, it sent the location and the health parameters to the doctor, so that the healthcare givers, they can reach there at an early stage. Okay. So then again, research, we can employ these biomedical signals for developing new technologies, okay, new healthcare technologies. So now coming to the biomedical signal processing, now you have understood what is a signal, what is signal processing, what are biomedical signals. Now, what do we expect in biomedical signal processing? So in biomedical signal processing, it involves applications of various techniques to analyze and interpret biomedical signals. Okay. So as you all know that these signals are being generated by the physiological processes of the human body. Okay. So the main goal of the biomedical signal processing is to extract meaningful information from these signals, enhance their quality, and enable accurate diagnosis, monitoring, and treatment. Okay. Now, key objectives of biomedical signal processing. First one is noise reduction due to the use of the filtering techniques, feature extraction. So it is basically the information that are being hidden within the signals. So we want to extract those information. Then compression, segmentation, okay, then pattern recognition, and then time frequency analysis. Okay, so these are the key objectives of any biomedical signal processing techniques. So application of the biomedical signal processing, ECG analysis, EEG analysis, EMG signal processing, medical imaging and image processing, telemedicine, wearable health devices, and biomedical research. So what are the challenges in biomedical signal processing? The first and foremost challenge is the variability. So your physiological parameter is different to me, which will be different to any of you. Okay. So in a population, if you see, if I say that two people will be having same physiological parameters, it's next to impossible because everyone is different, everyone's physiology is different. So we cannot expect that everything would be same. So there would be certain changes. Now these certain changes brings variability within the population. Okay. Then noise and artifact. When we are acquiring the signal, that signal may be corrupted with some noise or artifacts. Artifacts means unwanted signal components. For example, when the acquisition is being made, if I move, so what will happen? The electrode which has been placed on my body, it will move, and if it moves, there would be a noise which will be incorporated, and that noise is due to the human error, and hence it is called artifact. So any unwanted signal component which has been incorporated in your signal due to the man-made errors, then it is called artifact. So this is the difference between noise and artifacts. Noise, it will automatically come from the environmental interaction of your signal processing signals. Okay. Say for example, I am acquiring the signal just near the power line. So there will be power line interference. Okay, so that is a noise that due to myself, my error, that signal is not coming. Okay, but if I move and the electrode moves, that noise, it is an artifact. Okay, then lastly, real-time processing. So as I told you, there will be variability. So design in devices for various applications like ICU monitoring and other thing, it may provide an timely insight, but since there is a variability, what range would you select? So there might be a challenge. So what is the optimal range you will select and you will use to classify that the patient is not, or the the patient is not suffering from any kind of disease. Okay, so these are some of the challenges that are being associated with the biomedical signal processing. Now coming to the course content. So in the course content, what happens is that first I will be going through the introduction to the signals and systems. It would be a basic thing. So I will try to complete it into 2 to 3 days. Okay. So not more than that. It is a 3 credit course. So we usually have around 30 classes. Okay, in a semester. But the problem is that we are already into the mid of August, and we have lost almost 1 month. And again, thereafter, what happens is that you'll be having puja holidays and all these things, mid semester examination and semester examination. So it gets a bit difficult to get the 30 days over there. Okay, so but as you will find in your class, people are from the different backgrounds. So giving an outline of what are signals and systems and what they are expecting in the course, it becomes customary. Okay, so we will start with the basics of signals and systems. Okay, then once we go into that, do that, then we will be going into the introduction to the transforms. So we have discussed about the different transforms. So again, I will not cover this in depth. Okay, so we'll be discussing about Fourier series, Fourier transform, discrete time Fourier series, discrete time Fourier transform, discrete Fourier transform, Laplace transform, and Z transform. Okay. Now, after covering these two, we will be getting into the main signal processing thing. So over here, we will be first discussing about the basics of digital filtering. Okay. So over there, we'll be discussing about the sampling, digital filter operations, the rubber membrane concept, filter design by placement of poles and zeros. Okay. Then filters, they can be of two types: IIR filter and FIR filter. IIR filters are um, this infinite impulse response filter, and whereas FIR filters means finite impulse response uh, filters. Okay, so what is the difference between that? So you are in a group. So if you ping someone, so he may give a response for a prolonged period of time. Okay, he may get angry on you basically. So in a system, if you give an impulse input, and if the response is for a prolonged period of time, then it is called infinite impulse response. Okay. However, if you ping someone, he and if he gets angry, and within a couple of minutes he gets relaxed, then it is called finite impulse response. You have pinged him, but he has momentarily gone to a high excited state, but his output, it has come down significantly within a couple of minutes. So similarly in filters also, when you give an impulse input, what you will be having is that either the response will be for a prolonged period of time, or it will come down very quickly. So if it comes down very quickly, the response comes down very quickly, then it is called FIR filter. and if the output response is for a prolonged period of time, then it is called IIR filter. So we'll be discussing about the different types of filters over here, how to design those filters. Then we'll be discussing about the signal modeling, ARMA, ARMA and ARIMA. Then next we'll be going for the time frequency analysis, STFT. Then we'll be talking about Heisenberg-Gaber inequality, the Wigner-Wille distribution, wavelet transform and wavelet packet distribution. Then we will be discussing about the DSP architecture, hardware architecture. So the design methodologies, microprocessor architecture 8085 and 8086, and overview of the programming. Okay. So this will again be discussed in very brief. The but why it is necessary? This is necessary because some of the students are from non-engineering background. So uh, because of that, it will be discussed in this thing, because when they will be going for the biomedical instrumentation and other courses, in higher level courses, uh, they need a basic understanding of this one. Then application notes, we'll be discussing about the ECG signal processing, HRV analysis, EOG signal processing, EEG signal processing, EMG signal processing, etc. Okay. So this would be your overall course structure. Now coming to the books to be referred. So digital signal processing, principles, algorithms and applications, fourth edition, John G. Kouakis and Dimitris J. Manolakis. Then discrete time signal processing by Oppenheim, digital signal processing by Tarun Kumar Rawat, then biomedical digital signal processing by Willis J. Tompkins, and lastly conceptual wavelets in digital signal processing by D. Lee Fugel. Now the evaluation, as I already told you, we'll be having a mid-sem examination. It will be of 30 marks. Then we'll be having an end-sem examination which will be of 50 marks. Now next comes the teacher's evaluation. Now from this semester onwards, there would be uh, two components. Okay, so why it is coming? It is coming because of the curriculum changes. So the classical one would be class notebook, 5 marks whatever you are noting down. Then class tests, it would be of 5 marks. So there would be I will try to take at least 4 exams, and out of these 4 exams we take the best 2 marks out of that. Okay. Then every week from next week onwards, you will be getting assignments. So you have to maintain a separate copy for that. So assignments, it would be 5 marks. And lastly, there would be a flipped class. So this flipped class, basically, either I will be giving you the topic, or you have to choose your topic and get it approved, and then you have to give a presentation. Okay. So this is the first modality. And the second thing is that either you go for this one, or the second one is design an entrepreneurial activity, 15 marks, and class notebooks, 5 marks. So over here, what you have to do is that you have to design anything which is related to this biomedical signal processing. Say you need to devise a small device. Say for example, you want to develop a pulse oximeter. Okay, so you have to develop a working model, and based on that working model, you will be getting this design and entrepreneurial activity marks, 15 marks. So either anyone you can choose. So this is it from my side as of now. Now let's start with the next topic, signals and systems. What is signal? What is signal processing? I have already told you. So what is this analog signal processing? I told you, but you just have it look at it visually. So we have this input signal, which is an analog signal from the human body. Then we put it into the electronic circuit. So the output, it is the process output signal, and it is also analog. Okay. So input is analog signal, output is analog signal. So it is called analog signal processing. Okay. Now in the digital circuits, when we take the signals into the digital domain and use the microprocessors and microcontrollers, then it becomes the digital circuits, and then it is called the digital signal processing. Okay. So what are the advantages over here? Flexibility in the configuration of the DSP operations. They are usually accurate. Easy storage would be there, and these are cost effective. Okay. I'll be a bit faster in my lectures. Uh, you please go through the online lectures from 2023. Over there, you'll be getting the things in detail. Now again, digital signal processing. So what we have the signal from the heart. Okay. Then if you see, we are having analog to digital converter, and prior to that we are having anti-aliasing filter. So why this anti-aliasing filter is needed? Anti-aliasing filter is needed to band limit the incoming signal. Okay. So that the signal, when we take it into the digital domain, it is not aliased. Okay. Aliased means corrupted. Okay. So it is not corrupted. Why this corruption happens, we will be discussing at a later stage. Okay. Now once it is being digitized, then we use this digital processing unit. Okay. Now once it is being processed, if you want to generate the analog signal, so what you can do is that we can use digital to analog converters, and then we will be having this reconstruction filter. Okay. So this complete setup, it is called digital signal processing, because at the core we are having a digital processing unit which will be processing the data. Now I have an important question for you. What is the difference between analog signal and a digital signal? How an analog signal, hmm, analog thing also it is. So how an analog signal can be converted into digital signal? Forget that. What is the difference between analog signal and continuous time signal? Analog signal and continuous time signal. What is the difference? How many of you are from biomedical engineering background? No, electronics, electrical, electronics, electrical. So what is the difference between analog and continuous time? The signals. Are they same? Then what is the difference? The difference is that analog signals, they can have amplitude ranging from minus infinity to plus infinity. Okay, so they are called analog signals. Continuous time signals, if you put a sensor on my body for getting the, say for example, the thermistor, and measure my body temperature, it will be a continuous time signal, but it will also be an analog signal. Okay, it will also be an analog signal, but the opposite is not true. All analog signals are not continuous time signals. Okay, so why I am saying this? So if you see over here, the signal is continuous time signal. After anti-aliasing filter, we have this continuous time signal. Then we are having this analog to digital conversion. So in any ADC, it performs two functions. The first one is sampling, and second is quantization. Okay, in sampling what happens? This is the signal. At regular intervals we will be taking the amplitude values. It is as simple as that. So when you do that, it becomes a discrete time signal. When you do the sampling, it becomes a discrete time signal. Okay. Now it has become a discrete time signal, but it is still an analog signal. Okay. it becomes digital signals once we go for the quantization. Then it becomes digital signal. Okay. So up to sampling signal was analog signal, because the amplitude value could have been in the range of minus infinity to plus infinity. Okay. Then what we have after the digital signal has been there, so we have quantized it because there are specific values which a signal can take in digital signals. Okay. So if you are using a system, digital system, which works in the range of plus minus 10, so the maximum value that a digital signal can have is plus 10 volt, and the minimum value would be minus 10 volt. Okay. So it may be plus minus 20 volt, it may be plus minus 30 volt, it depends on the digital systems. So there would be a limitation of the voltage, up to how much it can go. That is the first thing. And second thing is that within this limit also, the voltage range will be specified. Say for example, if it is a plus minus 10, say for example 0, 1, 2, 3, 4, 5, let us say plus minus 5 volt for the sake of understanding. 1, 2, 3, 4. Then minus 1, minus 2, minus 3, minus 4, minus 5. Okay. So if the amplitude value is say 0.5, it will be rounded off to 1. If it is 0.49, 0. Okay, it would be 0. So if you see, even a 0.01 volt difference, what is happening? There is a marked change in the values. So we are incorporating some errors, and it is called quantization error. This error is called quantization error. Okay. So what I mean to say is that digital values can take only the prefixed values. They cannot take any values outside this, the prefixed values. Okay. It may be 0, 0.5, 1, 1.5, 2, 2.5. So there would be a delta V interval. Okay. So 0 plus 0.5, 0.5 plus 0.5, that means 1, then 1 plus 0.5. So by that delta V, the increment or decrement of the voltage would be happening. Okay. Now once it has been processed, then we get into the digital to analog filters. Now again over here in digital to analog thing, two things are happening. So in the digital to analog filters, what will happen? It will convert the digital filter to the analog domain. Okay. So it is capable to have any kind of amplitude value, but the signal would be discrete time signal. Similarly over here in sampling, after sampling you got discrete time. So similarly over here you will be having a discrete time signal. Now this reconstruction signal, it helps you to convert. So over here you are having dt. So this reconstruction filter, it will help you to get to the continuous time domain, and this is basically a low pass filter which helps in the generation of the envelope. Okay. Now comparison between these things, these are just basic things, just go through that. Applications, we have already discussed the different applications of the DSP. So classification of signals, by this time you must be knowing what is the difference between continuous time and discrete time signals. Then analog and digital signals, then real and complex signals are there, deterministic and random signals are there, even and odd signals are there, periodic and aperiodic signals are there, energy and power signals are there, causal, non-causal and anti-causal signals are there. So continuous time signal, when you do the sampling, we get discrete time signals. Okay. So some examples are there. So please do the thing. Whenever you do some mathematical operations, this arrow, it indicates that the origin value. Okay. So in continuous time, the time is represented by t. In discrete time, the time is represented by n. Okay. So when n is equal to 0, that means you are at the origin. So how do you define that? We define with this arrow. Okay. And when we want to do some mathematical operations, so if you see x1n and x2n both are there, so we have to match the origin values and then do the addition or subtraction or multiplication, whatever you want. Okay. So this you keep in mind. Then again, if you want to plot the result, so 0, 1, 2, 3, 4, n will be going towards the right hand side, towards the negative side also, and then just put the values 1, 3, 5, 4, something like that. So you will be able to plot the values. Then analog and digital signals, I have already told you, sampling, quantization. Okay. Then how this delta V is being calculated. This delta V, it is being given by 2 into V divided by L. What is V? I told you that plus minus 10 volt, plus minus 20 volt. Okay. So this 10 would be coming. Say for example, we are working with a plus minus 10 volt system. So we will be getting 2 into 10. Okay. Then L means how many intervals you want. Okay. So based on that, we call it as an L array signals. Okay. And usually it is in the it is having a value of 2 to the power n. Okay. So if it is 1, so what will happen? 2. So delta V will be 10. So if you look into this axis, minus 10, plus 10, so only 2 levels. This is 0 volt, delta V1, delta V2, only 2 levels. If it is 2 to the power 2, so it will become 4, so it will become 20 by 4. You will be having 5 things. Okay. Now over there the 0 will not be a 0. Okay. So 2 to the power 3, 6. So 10 by 6. If that happens, something 3.33. So it is not an exact value. Again, you will be having, you may have some problem. So 3 to the power 4. In that way, you have to increase the values. Okay. So once you increase the values, in that way you will be able to get the delta V value. When it is 2 to the power 1, you will be having only basically 3 levels, 0, 10 and minus 10. In that way it goes. Okay. Then real and complex signals, if any signals they are having this J, which is a complex number, nothing but under root of minus 1, then it is a complex signal. Usually the frequency domain signals, they are complex signals. And real signals, this J component will not be there. Then deterministic and random signals. Deterministic means it can be governed by a mathematical form or mathematical equation or a graphical form, whereas random signals, they are usually been defined using their statistical or probabilistic distribution values like mean, mean squared values and so on. Then even and odd signals, So what is even and odd signals? If x of minus t is equal to x of t, then it is regarded as even signals. So the common example is cosine signal. So if you see x of t, if you consider this point, so this is x of t. Again, if you consider the mirror point over there, so it is x of minus t. They are having same values. So it is an cos signal, it is an even signal. If x of minus t equals to x of minus of xt, sinusoidal signal. If you see, if you consider this point, this is x of t, x of t, and this is x of minus of t. Now if you look into the value, x of t is equal to minus of x of minus t. Okay, so the sinusoidal signal, it is an odd signal. So some examples are there which has been explained in the previous video. So this is also another example. So let's move forward. Then this equation is there. Any signals, they are basically composed of a combination of even and odd signals. It has been given over here in this way. So what is that? So when we talk about the even signals, even signal is nothing but xn plus of x of minus n. Okay, and odd signals xn minus of x of minus n. Okay, so suppose this is the xn. So this is the origin. So 1 5 3 4 2 5 2. So if you have to calculate the x of minus n, so keep the 4 as the same and then reverse the values. So this 2 will come over here, this 5 will come over here, this 2 will go over here. Then on the other side you will be having this 3. Just invert the values. Okay, so you get the x of minus n. Now for the even signals, xn plus of x of minus n you get, and for calculating the odd signals you get xn minus of x of minus n. Okay, so periodic signals and aperiodic signals, sinusoidal signals, they are periodic signals. Then any other signals which is not having any periodicity, they are regarded as aperiodic signals. In terms of mathematics, x of t, if it is equals to x of t plus t0, where t0 is the time interval, or time interval, or the period of the signal x of t, then it is a periodic signal. And if any signal does not follows this rule, mathematical formula, then it is an aperiodic signal. So this is an example of periodic signals. Okay, so some numericals are given. Energy and power signals. So energy signals are given by E equals to some this integral of minus infinity to infinity modulus of x of t whole square dt. Whereas power signals, they are given, the power of the signals are given by limit capital T tending to infinity 1 by t integration of minus t by 2 to t by 2 modulus of t whole square dt. Okay, this is for the continuous time signals, and for the discrete time signals, these are the equations. Okay, so an energy signal, it is having a finite energy. Okay, on the other hand, for the power signal, it is having a power and a finite and non-zero power. Finite and non-zero power. Okay, and also the energy of the power signals, it would be infinite. Energy would be infinite. Okay. On the other hand, the power of the energy signal, it is 0. Okay, so if you look into the energy signal, energy is finite, power is 0. On the other hand, for the power signals, power is finite and energy is infinite. Okay. If any signals does not meet this criteria, then they are regarded as neither energy nor power signals. Okay. So difference between the energy and the power signals have been given. So these are some of the examples how to calculate the powers and the energy of the signals. So here also there is another example. Okay. Then we have causal, non-causal and anti-causal system. So how do you define? So this is the zero time, and then 1, 2, 3, 4 like that our n or t goes. So any signal which is a right-handed signal, it is called causal signal. Okay. Non-causal signals, what happens? When the signal starts before the origin. Okay, let me draw it in with the blue. If the signal starts before the origin, then it is regarded as non-causal. And anti-causal, these are the signal which are opposite to the causal. In the causal one, the signal started from 0 and it went up to infinity. Anti-causal means it will start with 0 and it will go to minus infinity. Okay. So some of the useful signal operations: signal shifting, time scaling, time inversion, reversal, which is also regarded as a reversal, and combined operation. Time inversion, I have already told you. That means when you convert xn to x of minus n. Okay. Now let us see what do you mean by time shifting. So ft to ft minus a. So see the signal, it is being shifted towards the right hand side. So this value, say for example, over here you are having this value. This value, it has shifted to the right hand side of the original signal. So it is time shifting. Okay. Time advancing, it is given by f of t plus a. In other words, t minus of minus a. T minus of minus a. So that means it is going on the left hand side. So if you see this value, it is going on the left hand side. Okay. So these are the two ways of time shifting. One is delaying the signal, which is basically your signal is appearing after the origin. On the other hand, signal advancement, where the signal is appearing before your original signal origin. Okay. So this is an example. F of n over here. So this is the origin. Now what would be f of n minus 2? That means the delay. So if you see the origin, if you look over here, so what is happening? Value has moved to the right hand side. In comparison to this one, this modified signal, what is happening? Origin is on the left hand side. Okay. So this is the thing. So this was your original thing. So our A is 2. So we will put the new origin at 1, 2. Okay. Now for advancing, it would be the opposite. This was the 3. Origin has moved to 1, 2. Okay. You please try to understand this concept. This should form the backbone for you for the whole semester. Okay. Now time scaling, ft equals to f of at, and ft, if it is transformed to f of t by a, so it is called stretching, and f of at, it is called shrinking. So the most common example is in any videos we can put the video as say 1.5x. So what will happen? The video will be completed within a short span of time. Okay, so the signal is shrinking. Okay, so that is called shrinking of the signal. Now if you put it as 0.5x, so what is that? Time will be longer. So 0.5 I can write it as 1 by 2. So if you generalize it, you can write f of t by a. Okay, so the signal has been expanded. So you need to understand this. This is a bit confusing, both the things, both time shifting and time scaling. Okay, now you have understood this. Time inversion we have already discussed. Now, yeah. Now we will be going for the combined operation, where we may have operation like x of at minus b. Okay, so how to do this? So say for example, we have to calculate f of minus 2 and minus 2. So how will we do? So first what we will do, from fn we will go for f of n minus 2. So our origin was here. So this was our origin. So we have to advance the signal by 2, 1, 2. So this has become now n minus 2. Okay. Now 2n minus 2. Okay. Don't take it as 2 multiplied by n minus 2. Now your time scale has changed. So it is your 2 of n minus 2. So 2 of n minus 2 में हमारा क्या हुआ था? Shrinking. So from this origin, you keep the origin value like this, and then you have to take every second value. So first value I will cut, I will take the second value. It has come. After the origin, 4 I have deducted, 2 will come. 3 I will cancel out, we will get this one. 1 will cancel out, 3 will come. You getting my point? Now our signal is f of 2n minus 2. So this is our thing. Now we are having a minus sign. Just have to invert it. See, 5, it has come over here. Are you getting my point? So likewise you can do for the other things also. Over here if you see 0.5, 0.5 means what was there? Stretching. And when you are having this stretching, you have to put zeros. So after 2 there will be a 0 over here. Here if you see there is a 0. Okay. This is this is n plus 2 ना? हाँ, ये इसका n plus 2 is here. So after 2, see 0. Then we are having 3. Then after 3, it should be 0. So in that way it goes on both the sides. Are you getting my point? So time. No, we have crossed the time, so we'll stop today.